So today's topic is invariant bilinear forms, at least our starting topic. So let G be a Lie algebra over K. Then we recall the adjoint representation it's actually of G on G. And the zero representation I should specify here this is on G, and the zero representation is going to be on K. These define a G module structure on the K module which we're going to call N of bilinear forms on G. It's going to be sending two elements of G into K linearly. And then I guess we want to see which of these bilinear forms are invariant from before. Yeah, a bilinear form beta on G is invariant if it is invariant under the representation sending X to X acting on N. And this holds if and only if essentially beta of X bracket Y and Z is equal to beta of X and Y bracket Z. So essentially we can shift the bracket over to the other side. Now let D, okay, now we're not going to write it like that. So now the identity representation of D, which we're setting equal to the derivational algebra of G, and D, which is sorry, I had to check there, and the zero representation of D on K define a representation D to D acting on N of elements of D on our bilinear forms of G on K. And so we see a bilinear form of G is completely invariant if it is invariant under this representation, of the derivations acting on the bilinear forms. Which implies it's regularly invariant. And so a bilinear form of G is completely invariant if and only if beta of dx y plus beta of x dy equals 0 for all x, y, and g, of course, and d, I wrote it with a capital on the left, I don't know why I didn't do that on the right. And our capital B, D being any derivation. Here's a proposition for you. We're going to let G be a Lie algebra. With an invariant, symmetric, bilinear form. I'm guessing symmetric means that its arguments commute. And we're going to call this bilinear form beta, as always. And G also comes with an ideal A. Here are the three parts of our proposition. Part A, the orthogonal A prime of A with respect to beta is an ideal of G. If A is characteristic, which means it is invariant under, it's invariant under all derivations, not just the inner ones. And also beta is completely invariant. So it is also, it has this property on derivations. Then the orthogonal A prime is itself going to be characteristic. Condition C. If beta is non-degenerate, the intersection of A and A prime is commutative. Alright, let's look at the proof of this here. We're going to let D be a derivation of G. And with the constraints that A is stable under D, and beta dxy plus beta x dy equals 0 for all x and y, so essentially it's completely invariant for this specific derivation. Then, if z is in the orthogonal of A, this implies that the derivation of z is in A prime, since for all t in A, dt is in A, thus beta of dz in t is, as we see above, equal to negative beta of z and dt, which is in A. Since z is orthogonal to it, this has to be 0. So, which means A prime has to be stable under D. Every element in, essentially taking the derivation of A prime doesn't change its orthogonality, as we see. Thus we get conditions A and B. Now we're going to let B be a second ideal of G. Such that the restriction of beta to B is 0. Then, for x and y in this B, and z in G, beta of the bracket of x and y and z is by this writing of the derivation, this writing of the constraint of being invariant. This has to be beta of x and y, z. But x is in B by assumption, and y bracket z is still in B because y is in B and B is an ideal. Since the restriction, which means beta is acting on two elements of B, which is what I meant by this restriction of B, I guess it should be B times B, and thus it is 0. So what is this saying? This first element is of the form the bracket of beta with beta, and we see here it is orthogonal to G. So if beta is non-degenerate, that gives us that B is commutative. Applying this to the intersection of A and A prime gives C. Alright. Definition. This is one we'll probably repeat because it is an important one. I'm surprised so little space is given to it immediately. So we're going to let G be a Lie K-algebra, and M a G module. Suppose that M as a K module admits finite basis. A finite basis, you know what I mean. The bilinear form associated with the G module of M, G module M, which is essentially saying it's a representation of G on M, is the symmetric bilinear form sending X and Y to the trace of the product of their actions on M. If the representation in question of X and Y on M is the adjoint, so this is essentially the product of the adjoint representations. You can think of that as matrices, since M has a finite, since the target of the representation has a finite basis, we can write it as a matrix. Then this is called the killing form. And I've seen, as I kind of alluded to before, I've seen a lot of texts emphasize the killing form pretty heavily. Which is kind of surprises me here. They don't seem to, well, they talk about it a little bit. There's a couple propositions regarding it, which we'll go through here, but just like a personal note here, keep an eye on this killing form. This is going to show up a lot, I believe. So, like I said, we have 3 propositions in this section. And then we're going to move on. Our first proposition here, we're going to let G be a Lie algebra with a G module M. Where M has a finite basis as a K module. And the theorem's that the bilinear form associated with M, actually the version of the killing form on this representation of G on M, is invariant. Well, proof is that we have the trace of the bracket of x and y in G as a acting on M times Z acting on M. I guess the matrix product in this context is equivalent to the composition of these actions as operators. Anyways, this is equivalent to, you can break apart this bracket into x, m, y, m, z, m. Minus y, m, x, m, z, m. This is essentially just, I said, breaking apart the Lie bracket with using the linearity of the trace to take the difference out of the immediate calculation. Which is equal to xm, y, m, z, m, and then my linear algebra is not the best here. What they do is they rotate these elements. I guess what they're doing is they're multiplying the left side by y inverse, ym inverse that is, and the right side by y normally, and that's preserving the trace. I will trust that is true. I don't know that off the top of my head. And this, as we see, is just xm, and then doing this last step in reverse, we get that the bracket has shifted over, which is good. That's what we want. Proposition. Suppose K is a field and the Lie algebra G is finite dimensional. I'm guessing with respect to K. Yes, indeed, over K. So we're going to let A be an ideal of G. Beta, the killing form of G, and beta prime, the killing form of A. Killing form is such a cool name. It's just because the guy who discovered its last name is Killing, which means it's probably not pronounced Killing, but I don't know how it is pronounced, so I'm gonna live my dream here. And then of course the theorem, you can probably tell what it's gonna say, that the killing form of the ideal is the restriction of the killing form of the full G, restricted to the ideal. And we have proof of this. We're going to let U be in the endomorphisms as a vector space of G leaving A stable. We're going to let V be the restriction of U to A, and W the endomorphism of the vector space G over A as a quotient passing our U to quotient. Then the trace of U is equal to the trace of V plus the trace of W by, and this is just like splitting up the basis. I'm just going to write that informally. The idea there is to take the basis of U, where the first however many elements are the basis of a basis of G, sorry. The first few however many elements are the basis of A, and the rest are then going to be the basis of the quotient. So then I'm going to let X and Y be in our ideal. And apply, it says the above formula. I don't know what that's referring to yet. To the case, I think that's just referring to splitting up the trace. U is the adjoint in G of X composed with the adjoint G of Y. Then V is going to be the adjoint A of X, of course, times the adjoint A of Y. And W is 0. Hence, beta of X and Y, which keep in mind is arbitrary elements of A, is equal to beta prime. We got one more proposition that is, about the killing form before we move on. So suppose K is a field with a finite dimensional Lie algebra G. Then the killing form form, which we're going to write, I guess, beta for some reason, of G is completely invariant. Which, if you remember from before, it means any derivation splitting across its arguments. So like beta of dx with dx comma y plus beta of x comma dy is just going to be 0. Let's look at the proof. Let D be derivation of G. And there exists a Lie algebra G prime containing G as an ideal of codimension 1, which essentially means we're taking G and we're adding on a single dimension to it. And it also contains an element x0 with the G prime adjoint of x0 being equal to this derivation. So essentially, d of x is just a bracket of x0 with x inside of G prime. And we're going to let beta prime be the killing form of this G prime. Then for x and y and G, we have beta prime of x, x0 with y is equal to beta x of x0 with y by definition. Keep in mind this is just beta prime is equivalent to just beta prime of the adjoint of x0 on x, which as we saw, well, it's negative if you flip these, and that's the adjoint in G prime of x0 on x, which is negative dx y, and then we can move that minus sign out to the front since it's bilinear. And then this is going to just be beta x dy. So beta prime dx y plus beta prime of x and dy equals 0. And as we saw above, from our last proposition, beta and beta prime agree obviously on G, where the version of G identified with the ideal of G prime. So beta is just equal to beta prime restricted to G times G. And we are done, because it's still going to be 0 there. Alright, I think we have time to at least start a new I think we can probably get halfway through it, maybe. Or maybe I'll just power all the way through it. We'll see. I like going through an integer number of chapters each day, if I can help it. So our new topic is the Casimir element, and that is not how you spell Casimir. Let's look at our proposition. Let G be a Lie algebra over field K with enveloping algebra U H and G a finite dimensional ideal of G and invariant bilinear form beta with the restriction of beta to H being non-degenerate. Which I should look up. I'm pretty sure that's just, it means it has a non-zero determinant, right? Now we're gonna pick out two bases for H. One we're gonna call E, and the other we're gonna call E prime. Both have n elements. These are bases of H. Such that beta of two elements is just of the bases. Essentially, writing beta through these two bases gives it as the identity matrix. So it's 1 if the indices match up, 0 if they don't. Then the element C, which is the sum of the product of diagonal elements. This is of U, belongs to the center of U, and is independent of our choice of basis. Now keep in mind that since our bilinear form, invariant bilinear form beta is picked ahead of time, our first basis determines the second up to something, because we go element by element in our basis, and we need essentially the corresponding term, the other basis, to be one whose image under beta with the first is 1 and is linearly independent from every other element so far chosen. And let's prove this. And the C is of course going to be, in certain contexts, our Casimir element. So proof. For X and G, let XH be equal to the restriction of the G adjoint representation of X to H. Then the map from X to this representation is a representation of G on H. So I guess the point is this is like, I don't know if this would be the adjoint H representation of G if X is in H, but the point is it works even if X is outside of H. And beta prime, which is the restriction of beta to H, is invariant under this representation, which is just inherited from beta being invariant in the parent structure. Okay. By a homework question they have, so we can show, but won't immediately at least, that this element, the element EI tensor EI prime is independent of the choice of our basis EI, and is an invariant element of the tensor algebra of H. It is an element of the tensor algebra of G, which is invariant for the representation from the start, which is the restriction of the adjoint to H. Its canonical image in U is C, which is independent, therefore, of basis, EI of course, and is an invariant for the representation of G on U. Making it permutable with all of U. All right. When beta is the bilinear form associated with G module M C as defined above is called the Casimir element associated with M. So I'm guessing beta in this context is the version of the killing form in this context. And C exists even if the restriction of beta H, no, not even if, it restricts F B restricted to H is non-degenerate. Alright, is it worth it to keep pushing on? Yes, it is. We have one more proposition. Okay, last section of the day, one more proposition. We're going to let G be a Lie algebra over a field K H and G an ideal of finite dimension n is going to be its dimension, and M a G module of finite dimension over K. And we're gonna now let C be the Casimir element which in this context we're going to assume exists. Associated with the M, which is essentially a representation of G on K module M, and this ideal H. And your two assertions here. The trace of the action of the Casimir element in G module M, essentially the representation of this element act on M, is equal to the dimension of H, which is N. Second assertion, if M is simple, containing no substructures that are very stable under, yeah, you know what I'm getting at, and N, and the characteristic of K does not divide the dimension of H, then Cm is an automorphism of M. And proof, we have that the trace of C of M is the sum of the traces of EI prime of M is equal to the sum of the associated bilinear forms, which is our version of the killing form acting on e to the I prime, which is equal to n. Hence, if the characteristic of k does not divide n, I hope that is the right order to write that in. I have not taken number theory yet. Then, Cm is non-zero. Otherwise, I see. So if like the characteristic, if you're in like say char 2 and the trace is even, that's equivalent to saying the trace is 0. So it could just evaporate. Now, SC belongs to the center of U, where I'm guessing you use the enveloping algebra of G. Cm is permutable with all actions represented xm for x in G. You know what I mean? X acting as a function acting on M. And in our second case, if M is simple, then Cm is invertible in set of linear maps on M. And there we go. That relies on a proposition in a different book, which we do not have access to. And it seems to be common. Alright, so yeah, I think next time we will cover extensions of the base ring in the next video, and then we'll be able to move on to a different section in a different book, where we'll be looking at, I believe, the free algebras and free magmas in detail. So look forward to that.